Everything you see, everything you hear, it's all delivered to you by something that's, well, usually completely invisible. We're talking about waves. They are the universe's ultimate energy delivery service, and today we're going to pull back the curtain and see exactly how they work.
So, let's start with a real mind-bender. Imagine a star exploding billions of miles away. It's an event with just an insane amount of power. We can see the flash of light, right? But what do we hear? Nothing. Absolute silence. So how is that possible? Well, the answer is hiding in plain sight, in the very nature of waves.
All right, so to solve that mystery of the silent explosion, we've got to start with the basics. What is a wave, really? And I want you to forget about the ocean for a second, because we're talking about something way more fundamental. It's how energy moves through, well, everything, from the deepest parts of space to the very air you're breathing right now.
Okay, so here's the textbook definition, but let's break it down. At its heart, a wave is just a disturbance. Think of it like a little wiggle or a vibration that travels from point A to point B. And here's the most important part. Its one and only job is to carry energy along for the ride. But here's the part that's kind of wild, the bit that's a little counterintuitive. Waves move energy, but they don't move stuff. Think about a rubber duck or a buoy just floating in the ocean. A big wave rolls by, right? The buoy just bobs up and down, but it doesn't actually travel to the shore with the wave. The energy makes it to the beach, but the water itself pretty much stays put. It's exactly like a wave at a football game. The motion goes all the way around the stadium, but you and everyone else just stand up and sit down in your own seats. Okay, so if a wave is just energy moving around, what's it moving through? This question right here, this is the key that cracks our whole mystery wide open. It all comes down to whether a wave needs a medium to travel. And medium is really just a fancy science word for stuff. Matter, something to travel through. And that little distinction splits waves into two big families. On one side, you've got your mechanical waves. Think sound or ocean waves. These guys are needy. They have to have a medium to travel through. They need particles to bump into each other to pass the energy along. But then, on the other side, you've got electromagnetic waves. Light, radio waves, these are the total independents. They don't need a medium at all. They can just cruise right through the total empty vacuum of space, all by themselves. And right there, you can probably see where this is going. The answer to our big mystery is starting to click into place, isn't it? Light is one of those electromagnetic waves. It doesn't need any stuff to travel through. So it has absolutely no problem crossing that vast, empty void of space to get from some distant, exploding star all the way to your eyeballs.
And boom, there it is. Mystery solved. The light from that star? It's an electromagnetic wave. So it's perfectly happy traveling through a whole lot of nothing. But sound is a mechanical wave. It needs particles to vibrate. It needs air or water or something to carry it. And out there, in the vacuum of space, there's nothing. No particles, no medium, which means no sound. Space is totally, completely, utterly silent.
Okay, so we figured out what waves are, and we know the two main types. Now we can dig a little deeper. Let's talk about how the particles actually move when a wave's energy passes through them. Turns out, there are two main ways this can happen.
First up, you have what are called transverse waves. The best way to picture this is to imagine you're holding a long rope tied to a doorknob. If you flick your wrist up and down, the particles of the rope are moving vertically, right? But the wave, the energy, travels horizontally down the rope. That up and down motion is perpendicular to the forward direction of the wave. And fun fact, all electromagnetic waves, like light, are transverse waves.
And the other type? That's a longitudinal wave. Now, instead of a rope, think of a slinky. If you push one end forward, you see this little bunch up, this compression that travels all the way down. The coils of the slinky are moving back and forth parallel to the direction the energy is traveling. And the classic example of this is sound. It's really just waves of air particles getting squished together and then spread apart.
All right, for our last section, let's get into the language of waves. How do we actually describe them and measure them? Well, it turns out scientists have a vocabulary for this, and it really boils down to three key properties that can define pretty much any wave you can think of.
First on the list is wavelength. You'll often see it represented by the Greek letter lambda. And it's exactly what it sounds like. It's the length of one full wave. The easiest way to think about it is measuring the distance from the top of one wave, we call that the crest, to the top of the very next one.
Next, we have amplitude. This is all about the wave's height, measured from its center point up to its crest. Really, amplitude is just a measure of a wave's intensity or its energy.
So for a water wave, a bigger amplitude means a taller, more powerful wave. For light, a bigger amplitude means it's brighter. And for sound, a bigger amplitude means it's louder. Simple as that. And last but not least, we have frequency, which we measure in hertz. Frequency is all about timing. It's literally just counting how many complete waves pass by a certain point every single second. So, a high-frequency wave is wiggling up and down really, really fast, and a low-frequency wave, much slower, much more chilled out.
So when you put it all together, you realize something pretty cool. You are literally swimming in an ocean of waves right this second. The light hitting your screen is a wave. The sound of my voice reaching your ears is a wave. And every single one is a little packet of energy, defined by its own special wavelength, amplitude, and frequency. It really makes you think, doesn't it? What other energy, what other invisible waves, radio, Wi-Fi, you name it, are passing right through you in this very moment?